Hey everyone. We're going to start out with some very brief computer science history that we need because we're going to go over the game of life, which is a very big topic in the history of computer science. And for those of you who graced me with your presence during office hours, we went into a lot of computer science history. And we talked about two people. One of them is John von Neumann. He's originally from Hungary. That name is not Hungarian, that's German. He was a member of the Hungarian nobility. He came from a very rich family and had good teachers. So he was a child prodigy and he basically knew calculus like really early. And he did a lot of stuff. None of this will be on a quiz, hopefully ever. But things like the computer virus and EDVAC, one of the first computers ever made, self-replication, von Neumann ordinals, those like some of those you might have heard of, some of them you might not have, like the von Neumann universal constructor. We've heard of a constructor. Uh, it kind of resembles what he did. It kind of doesn't because this was in 1940s and computers didn't exist back then the way we think of them now. And then there's one more note about John von Neumann. He's not a bad guy. He's not like the Darth Vader of computer science, but he did have a very significant role in creating the atomic bomb, and a lot of people have never forgiven him for that. I will let you decide what you want to feel about nuclear proliferation, but he is the person who decided that the best way to maintain world peace was just to give everyone nuclear weapons and hope they're polite with each other. Then there's Alan Turing. He's on a piece of paper that's worth money, just like Benjamin Franklin, the discoverer of the electron, which we also need for computers. Alan Turing, just like von Neumann, grew up and worked on mathematics and computers when computers were turning from an idea into actual things. Alan Turing, like John von Neumann, was active during World War II. He worked in cryptography. He broke codes. One of the ciphers, several of the ciphers, but one in particular that the Nazis used was recovered by the UK, the British, and he broke it. And we were able to figure out where a lot of Nazi units were. And we kept it a secret. And it's very possible that without Turing, we would not have had that strategic advantage. He's known for the Turing machine. I say the Turing machine because it's a generalizable concept that we modify. He's also known for the Turing test. If you've ever seen the movie Blade Runner, the void conf test in the very beginning is basically a Turing test. It's a thought experiment where you're trying to figure out if an agent is a human being capable of doing a task that human beings are known to be good at doing, or if it's a computer imitating such a person. He basically described the modern digital computer and invented artificial intelligence just in like 2 papers in his 20s. No big deal. Unfortunately, he was treated very badly in his later years. He's on a banknote for £50 today. So over time, his reputation was rehabilitated, but combined with his work on the war effort and his poor treatment, for a long time, no one had heard about him, no one cared about him, and no one knew what he did. Today, which is better than World War II, we study Turing and logic, cryptography, obviously, cybersecurity, mathematics, philosophy, linguistics, psychology, neuroscience, biology, medicine, and computer science. It's like not even a joke. Like his ideas have very far reaching implications. Even though he didn't do like the laundry list of things that von Neumann did, the impact of his work changed the world dramatically. One last thing, in his later years, he got interested in computational biology, which wasn't a field. He was in the 40s. If any of you like biology, you'll know that the structure of DNA, as we know it today, was not finalized in its description until the 1950s, the early 1950s. Two people won a Nobel Prize for it, even though a lot of other people were working on it before then. The idea of self-replicating information as a model of life in the 1940s coming from computer science was big because independently in biology, they were trying to grasp the same thing. But because these two groups of scientists weren't talking to each other, they went totally different directions with it. We're going to look at the computer science direction. So this is just like kind of like a refresher. We know we write our programs in languages. We're using JavaScript with the p5.js library. We haven't really gone into how this works, but we can write those programs as zeros and ones, and then a computer can run it. We're not going into how that works. We're just going to assume that that's how it works. We also know, and this is very subtle, we know that computer science is a science. Why? Well, science is in the name. That's like good enough for me, right? In sciences, we observe what happens, like in nature, but on the computer too. Computers are just like rocks that we smash together a lot of times and then like blasted with some impurities to make them perform in a certain way. And they do things when we turn them on. But, there are still things we have to observe. So we come up with hypotheses, which is just a guess that we can basically run through some tests to see if we should reject that guess, or maybe that guess isn't bad. And then we make general conclusions about computers. So I'm going to rehash what we already know. A computer starts the initial state, like your memory, your transistors, they're all in a certain state, high, low, a lot of highs and lows. We have inputs, we have the values of our variables in their initial state. And then a specific procedure happens, like a function is called, or a bunch of things are drawn. I'm going to call that a recipe. I'm not going to call it an algorithm, but it is an algorithm. But we're going to call it a recipe. And then at some point, the computer either finishes running, which we're going to call halt, and outputs some information. That information is your output, but also think about like the state of the memory, the state of all your variables, where things ended up when the program halted. So nothing so far stops us from modeling very simple computer things, like recipes, within another computer. We've already been doing it with p5.js. We're modeling a canvas inside of a computer. We could take a step back further and maybe like think of like how we could abstract it in other ways. And the corollary to that from real life is, at some point deep in the past, in World War II, 80 years ago, the term computer meant the person, like the job title, the person who was doing the computation of mathematics using an electronic device. Somewhere along the line, we said, okay, let's take all the things that the computer, the person does, and let's have the device that they were using actually do those things. Then we don't have to hire those people anymore. That sucks for them, but that's what happened. I wasn't around for it. I had no say in it. But what happens is when we start replacing things that do repetitive tasks. Anyone who's done, pre-calc will say math is a lot of repetitive tasks. When we have repetitive tasks, we can model them using automata or automatons. If you've ever seen a cuckoo clock, that's an automaton. If you've played Five Nights at Freddy's, those characters in it, those are animatronics. Those are electric automatons, meaning they're powered by electricity, not just mechanical motion. So an automaton is a self-operating machine that automatically follows a predetermined sequence of operations or responds to predetermined instructions. I'm curious if we can, take the talk about a machine and just make it a program. And that way we could, instead of having a machine that runs a program, we can have a program that runs another program. It's still kind of subtle. I'm still putting this idea together, but hear me out. So another extension to Cellular Automaton, and this one comes from our good friend von Neumann, is the Cellular Automaton. Now, this just extends it. So we have a grid of cells, like a chessboard, that each have a number of discrete states. Now, discrete just means it's on or off and no in between. So 0 and 1. We don't care about 0.4. We don't care about 0.33 repeating. we care about 0 and 1, and that's it. That's all that discrete means. These cells are arranged in an initial state. So some of them are on, some of them are off. They can all be on, they can all be off. Those are all valid. And they update themselves according to rules and according to their own contents and the contents of their neighboring cells. And we're going to see this a couple more times. But when I say neighboring, I mean all 8 neighbors, not the adjacent 4 and across. I mean like the full square around it, not the up and down, left, right. So I kind of mentioned this, but Turing and John von Neumann were interested in life as a kind of self-replicating information. John von Neumann took this a little far and basically invented the computer virus. Again, before computers existed, computer viruses were known by John von Neumann. But when von Neumann and Turing were thinking about life as self-replicating information, these computers were busy doing other things. It was the middle of World War II, and those computers weren't there for frivolous pursuits, to put it mildly. In the 1960s, when John H. Conway comes around, people started being able to just do whatever they wanted with computers. They had too many of them. They had a lot of old ones. They were still very expensive. But you could, you could work on it for 8 hours, and overnight you could run some simulation for yourself. You could have it predict the stock market or try to do something with it. So that's what started happening, was people started looking at the old ideas that people such as Turing and von Neumann had, and we're like, okay, well, now that computers are cheaper and faster and I don't have to just do businessy stuff with them, maybe I can do something else. So Conway started getting into the idea of games. And von Neumann was an economist along with a bunch of things, and he wrote a giant book about games. And it doesn't tell you what a game is. Do all games have rules? Some games don't. Do all games have boards? Some don't. Do all games have players? Some don't have players at all, and some have a lot of players, and some are just by yourself. So there's no technical definition for game. But, and John Conway noticed this, is that some kinds of games have the kind of rules that you can model in a computer and have the computer play them for you. And from John von Neumann, who had this idea of life as self-replicating information, Conway found the rough guidelines, like the criteria or the client specifications for what John von Neumann thought would be life. And these 4 criteria, I'm calling them rules, but we're going to look at some other rules. So, I'm just going to call them criteria. Let's not forget Johnny. So, no explosive growth. That means if you have 2 rabbits on day 2, there shouldn't be 20 million. Maybe there'll be 3, but there shouldn't be 20 million out the gate. There should exist a small initial pattern that leads to chaotic, unpredictable outcomes. Now, chaos is a scary word, but all it means is dynamic, changing over time and in a way that is unexpected. Just like the word says, it's not a bad thing. It's just we have less control over it than we'd like. And I mean, I brought this up before. This is before the Nobel Prize was awarded for the double helix structure of DNA. That Nobel Prize was 1952. This is 1940s, before John Conway. But the idea was that information would replicate more information. That's like saying in computer science, we're going to make a function that takes a function in and outputs another function. That's hard to wrap our heads around. But if we just generalize it to information and look at the behavior, then we can talk about it in terms of functions and all the other computer science topics we want to. And lastly, the rules should be as simple as possible. So John von Neumann had those guidelines. Conway came up with these 3 rules, which I called the recipe. I remixed it. We can do this in 2 rules, but John Conway said 3. I want you to do it in 3. The first rule is any live cell, that means it's on, high, 1, some number that's not 0. If it has fewer than 2 live neighbors, it'll shut off. It's lonely. The party has no one there. It leaves. It goes dead. Number 2, any live cell with more than 3 live neighbors will die. It's overcrowded. There's too many people at the party. The line is too long. That's the kind of metaphor. But it dies. It shuts off. It goes to 0. It becomes false. However you want to put it. We have a lot we can work with our Boolean algebra. The last one is different. So this works on dead cells, not live cells. Remember that. Any dead cell with exactly 3 live neighbors becomes live. We switch it on. It's born, it's spawned, it goes high, it becomes true, however you want to put it. And if you're observant, you'll notice that rules 1 and 2 can be rewritten in terms of any live cell with 2 or 3 live neighbors stays alive. That's a corollary. That's basically a rule that restates what other rules say. It's like a rule you get for free. But stick to the first 3. Okay, so now that we have a recipe, we need some ingredients. So we need a board or a grid for our cells. We already have arrays. We need on-off states. We have our Boolean logic. And we need our cells to contain some sort of state info about those on and off states. We have classes. The last part we need is a way to keep track of time. And we're going to keep track of time stepwise. That means step by step, not minute by minute, second by second. Just step 1, step 2, step 10 billion. There's nothing in between any of the 2 steps. So we got to let it simmer. That means we're going to update the program over time. Like I said, it's stepwise. That means hour by hour. We're not counting the minutes. We're just going from 1 to 2 to 3. Now, every time the clock ticks, the program is going to do a full check of every single cell, whether it's alive or dead. And that check is going to consist of checking the 8 cells around that cell. And for all of those cells, it's going to see which of the 3 rules applies. If the first rule applies, it doesn't have to check the next ones, obviously. It short circuits and just defaults to the first one if that one applied. But what we can see is we're already on the hook for 2 nested loops, like 2 sets of nested loops so far. Maybe we need more. But we're kind of translating the idea that John von Neumann had into John Conway's solution for the game of life. Because remember, he gave very specific examples of how many cells are live, how many are dead. He could have said 5, he could have said 10, he could have said any other number, but he chose those because of the outcomes and the stability of the game. Next, I'm going to use the technical terms stride and sweep. These are technical terms for going over large, annoying 2-dimensional arrays. Now, striding means we go line 1, or the first line, line 0. We go from element 0, left to right. Then we go to the next line, left to right. We're just strided, back and forth, stride. The other loop motion is sweeping. Now, this one, we're gonna see it, so don't worry about imagining it, but we're gonna start with a cell, and we're gonna go 1 up and 1 to the left, and start there and do the check, and just check all 8 adjacent cells. Sometimes the 8 adjacent cells are called the 8 neighborhood, and the 4 adjacent cells that form a T or a cross, those are called the 4 neighborhood. I'm not using those terms. I don't see those terms a lot, but maybe you like them. I don't know. Lastly, some of you might have noticed a problem. What happens when a cell is active and it's 0, 0, or some other thing that's on the top or bottom or left and right edge? So we need some sort of like way around it. If we're going to use the sub recipe, it's like making a roux or your crust separately. You can put anything you want in that crust. You can add that roux to anything, but you're making it separately. And those of you who went to the lab last week, we actually did edge detection. You can't reuse that code, but we did it. So this is not new to any of you. Okay, so lastly, our program or our experiment should resemble something like this. After a fixed number of ticks, which are discrete moments in time, the cellular automata, the cells in the grid, they're all going to be dead, blank grid. Or some will be dead, some will be alive still, and they'll be stable. They're not moving, they're on, they're not changing, but they're on. And if they're not stable, that can mean one of two additional things. One is that they're remaining in a pattern that repeats itself. And we call that repetition window a period. So if something repeats every 2 frames, its period is 2. If something just stays the same, technically its period is 1, but we don't talk like that. We care about things taking at least 2 steps, two or more steps to repeat. And lastly, and I'm not sure if this is possible in Game of Life, but it's very possible that in some circumstances you will basically have cells that stay on forever, don't repeat a pattern, but keep moving and don't have any sort of like repeating pattern. So it's sort of like similar to the digits of pi. They just keep going forever. They don't repeat. I haven't seen this in Game of Life yet, but it might be possible. So I just put that as an option. Usually what's going to happen is everything is going to die. I guarantee it. The first time I run this, I'm probably just going to have something die. What usually happens is people find really cool patterns and they want to repeat it and share it with each other. And so we care about 2 and 3, but mostly number 3. So I'm going to bold that. So I want to see some answers in Twitch. Based off of the description that I've given you, does the Game of Life have rules? I think this is an easy one. Does it have a board? Yeah. Does it have players? That's a tough one. It's built off of a group of automata. So technically has 0 players. The computer's doing it because we're using automata. Does the game have pieces? Okay, so people are saying that it has pieces. Some people are saying no. If the Game of Life has pieces, are the pieces moving? Or are they just going on and off and making it look like they move? Yeah. Okay, so that's a tough one. They look like there are patterns in Game of Life that look like it's moving. But these are cellular automaton that are flickering on and off. So the idea of movement is like life. We can come up with a very computer focused version of it that loses its meaning, or we can accept that there are things computers cannot model. I want to say we have something that resembles movement, even though they're technically not actually moving per se. They're just drawing a new drawing based off of the positions from an old drawing. So, oh yeah, last one. Does the game of life have a winner? Like, how do you win it? Okay. Well, I think that there's a winner, and I think the winner is all of us. So let's go back to the basics again. So, as you've noticed, we're not doing any code right now, but we've got some code right here. This looks like code, but it's just an example. So, the board is an n by m array. That means column by row. Just n and m are numbers. N stands for number, m stands for mumber. It's like number, but it comes after or before number. So this lets us think of cells in terms of their address. Where do I go to get this information? And it also lets me think of what's the information there. So we have two layers of abstraction. This might not make sense, but what does make sense and why you need to care is two layers of abstraction means we might need to bust out the box brackets and the dot operator because we have an array and a class operating at two different layers of planning this out. So we have to care about accessing an array, and we have to care about accessing some instances. So the board also provides visual output. That's kind of trivial, but you're not you're not exporting this to like some other output. Like the board is going to have the state change. You don't have like an array and then like some other thing drawing it. Like you want everything to be self-sufficient because the game of life was first published in 1970 in a magazine, Scientific American. Back then, that's how a lot of programs were distributed, was in a magazine, and you typed it out at home. So if this took like thousands of lines of code to work, that wouldn't be interesting. Like there's tons of games out there that have a lot of code and they're really complicated, and they still can't do what you can do in Game of Life. So let's think about what Game of Life is doing differently than something that was written in thousands of lines of code. So we have an initial state. Like I said, this is your inputs, but this is also what the starting values of your variables are. The other important part is the cells aren't yet updated. We haven't done anything yet. They might be on or off, but they're on and off because they started that way. Now, we're going to, in the homework, use the random function along with basically what's called a seed. If you've played Minecraft, you know what a seed is. It's basically a number that generates all the future numbers you generate. So in Minecraft, you type in a seed and it generates a unique map that's tied to that string of numbers. And anytime you use that specific seed, you get the same map. Even though it's called random, it's giving you the same thing each time. And that's actually what we want for scientific purposes. So I told you about Minecraft. But in the real world, using seeds is super important. My data sets, when I do machine learning stuff, like they can easily be like 30 gigs large. I can't email that. I can email a small part of it. So what I do is I sample something, and I want to make sure every time I use that sample, I can generate it from my original data. So the way I do that, and the way everyone in science does that, is using a seed. And that means that anytime I select 100 things at random from my big data set, it's the same 100 things, unless I use a different seed. So we're going to go back into like the basics of computers. And we assumed it's a mechanical device. We explored other mechanical devices like cuckoo clocks. Those are automaton, but they're not cellular automatons. We thought about parking meters a long time ago when we were talking about functions. Those things, those parking meters are kind of like computers. They take something in, a coin, you turn a crank, and then a flag pops up saying you're allowed to park, and then it counts down. What happens is we're starting in an initial state. A series of step-by-step procedures are applied, the steps in the recipe, and then at the end, the program alts, or it remains in a loop. And that's kind of like alting in a pattern. So it's like instead of just stopping on this one square, it's stopping on a square, and then it just like the square rotates until a full circle occurs. I've shown you that in 2 separate labs. I snuck that in there, but you've seen things that stay in a pattern without a loop. It's kind of tricky of me, but some of you understood what I was doing, so I was glad that you saw it. For those of you who don't understand, what I did was, for some of my animations, I used trig functions that basically just trace the shape of a circle. So instead of using a loop to make something move in a circular fashion, I'm just using something that just naturally oscillates. It's a hack, but it's a very elegant hack. We're going to see the same thing with Game of Life, where sometimes our designs, our automata, just repeat the same pattern forever. And they might move over one or two squares, but they're still repeating a pattern. So just be aware of that. It's hard to imagine other options. The only one I can think of is like some sort of like bizarre, chaotic explosion where your Game of Life simulation just like randomly generates new information. It has no repetitions and just does it forever. It's really hard to get that, but it's, that's on the table as a possibility. So another part we need is to think about is once the program alts, that is, the program it's not doing anything new. It stops or it's in a pattern. That's its alting state. It's like, this is the picture you could email to your grandma. Like this is where it stopped. I started here. It stopped here. It looks like this. I put this into the machine. It gave me that. So the other part we need is that it's not going to alt at a random number of iterations. It's going to alt at the same time. If you do long division on some big numbers, you can do it totally wrong and need more steps, but it's not possible to reduce it below a theoretical threshold if you're writing out all your steps. And it's the same thing with computers. Computers don't have a way to shortcut this. So it's going to go through one tick all the way to 10,000 ticks and then stop at that 10,000th tick if that's what it has to do. Sometimes it'll alt on the second tick. We don't know in advance, or so I claim, when any program will alt. We don't know if it'll alt at all. And these are the kinds of questions that are important for computer science. If you're shipping out a piece of software and it just, sometimes it just never stops running a procedure, that software is not sellable. It's got a major bug in it. So keep that in mind. So I've got a question. This might be a possible extra credit. I don't know. If I gave you just like a picture or an array and that was the alting state, like I gave you an array of zeros and ones and you had a program that loaded it, and I gave you the recipe for Game of Life, like Conway's 3 rules. Can you show me the initial state that I used to get there? Any ideas in chat? Okay. More generally, I could ask someone to write a program that takes any possible alting state, or like an arrangement of zeros and ones in an array on a grid. And then I can ask, how many ticks did it take and from what input state did we get here? That's a question that is important in computer science. So I'm not going to tell you the answer. Maybe next office hours I will. But keep in mind that is something that we care about. And if it went straight over your head, that's okay. I mean, we'll talk about it in office hours. But the idea is these computations run in one direction. Time runs in one direction. but these computations in game of life are not reversible. That's why we have to study them empirically, like through observations. So I'm going to leave this part before we move on to the next part of the lecture. Conway and Turing are great people. I don't think John von Neumann is bad. I just don't think he's a good role model. And so we're going to go on to the second part of the lecture, and I'm going to do some library science. You're going to say, okay, what does that have to do with computers? It has everything to do with computers. Library science is the study of information repositories, or GLAMs, galleries, libraries, archives, and museums. You're not just shelving books wearing cool looking glasses. Like, you care about information and how to archive it, how to retrieve it, how to search for it, and preserve it. In mathematics and computer science, especially the part where we're like weird enough to talk to each other, we talk about zoos, and those are basically like a gallery of mathematical objects that we need to talk about in both those fields. So I wanted to do the same concept for some of the first things you're going to see when we actually play around with the game of life. So okay, so the extra credit before you ask me again is a joke. It's unsolvable. Turing already solved it. It's called the halting problem. Read about that, and maybe you'll become an awesome computer scientist who like annoys everyone and just is like, you can't do that. Halting problem. Can't do it. Halting problem. You'll be the life of the party. Everyone will love you. You'll be like Jeff Goldblum's character in Jurassic Park. Anyways, this is what I call the sweep. This is a technical term, like we use it at NASA. It just physicists use it, not computer scientists. I like it though, because what I'm doing is this magenta is like a more violent form of pink. This magenta box in the middle, we care about that. We're not starting at the top left anymore. We're starting in the middle. That breaks the rules and the design pattern of p5.js. But we start in the middle and we sweep around the outside. We start at that middle. We go to the top left. That's -1, -1. We know that. In relation to the magenta square, that is -1, -1 of whatever the array value for that magenta guy is. That's as far as I'm going to tell you. If I told you any more, you'd be done with the homework already. But what we're doing is we're going in a counterclockwise fashion. Widershins, for those of you who know the other word for counterclockwise. And we check the state of each of those 8 neighbors. We do not care about the 4 neighbors next to it and above and below it. We care about all 8. So the first rule in Conway's recipe, it's usually called loneliness. Might be something else. Basically, all 3 of these yellow boxes, on the immediate next step, they're going to die. I can show that to you. Oh, another thing. This little squiggly thing, this stabilized in this pattern. It's run for over 2,000 steps so far. It's not changing. It's not going anywhere. So I can assume it's probably not going to ever change. So I drew something like this. What is going to happen when I press next? Let's see in chat. They will turn off. That's it. They're done. They got lonely. They left. The party didn't have enough people. They went home. Okay, overpopulation. This one also features rule number 3, but we're only going to care about the dying part when I draw this. So this is a 3x3 square. Bam. Next one, The center's gone. The four immediately adjacent neighbors are gone. The up, down, left, right. Those four, get this. These four, that's the von Neumann neighborhood. Like, even this has something named after von Neumann. It's so bad. Anyways, so you can see the rules keep getting applied. And I drew them too close, and now there's some weird thing. But that's cool. I like science. I'm going to keep this running. So that went away really quickly because I left my speed on too high. What happens is this collapsed into a stable pattern. And this is called an oscillator because it goes between two states. And just does it forever. There's more of them, though. There's a lot more. So we've seen overpopulation. Now, this is called birth or spawning. Now, the magenta tiles are the new tiles. So this has 3 steps: the initial phase, a second step, and then a third phase. So I'm going to draw that out. So next step, it's a 2x3 rectangle. The next step, it's kind of like a gemstone. So which of the other the first 2 rules happened here? Drop it in chat if you know. Yeah, it's overpopulation. So remember, we're looking at all 8 adjacent cells, not just the top, down, left, right, von Neumann neighborhood with only 4 cells. We're looking at all 8. So these are the basic shapes. These 5, and there's some others, but if you draw these shapes, they don't change. You can try this out. We're going to be trying it out at lab, so pay attention for a little while longer. I know it's hard. These just stay the same forever. They don't move. They don't get drawn next to their original location, making it look like they moved. They don't rotate. They don't exhibit a pattern. These guys do. These have a periodicity of, well, I'm not going to tell you. I want to see some answers in chat. What is the period of these? Now, the period is the number of steps. So if something repeats every 5 steps, it has a period of 5. If something just stays the same, it technically has a period of 1, but that's really boring, so we're not going to talk about that. Yeah, 2. Let's everyone else put 2 in the chat, so I think all of you are on it. These are just 2. So are there more? Are there any that are like thousands? People actually try to discover these on their own. And I said like the first publication of the Game of Life was in 1970. This apparently sparked a small cottage industry of people mailing printed out newsletters to each other where they would find new things. And that's where all the names for these went, or all the names for these started to come from, like gliders and spaceships. So gliders, I didn't pick that name. Someone else did, who discovered it probably. These repeat a pattern and express what we would call movement. Like I said, I don't think these are moving, and they're more interesting if you realize they're not moving. They're replicating information based on the previous state of the cell to make a new state of those cells. That is way more interesting than it just moving. So the lab is going to be very interactive. That's why I'm not showing you any demos. In the lab, we're going to all open everything, and we're going to find some stuff, and we're going to report on it together. And see, do a science, as they say. So I don't have anything else. We're going to end a little bit earlier, which means the lab is going to open up at exactly 7, possibly a little bit before then. I don't have anything else. Drop the slides link. I will drop the slides right now. I'll drop the slides during the break because it always takes me longer than I think it'll take. Yeah, that's it. I'll see everyone at 7.